We're ready now to talk more about vectors. Up until this point, we've been talking about linear motion, meaning objects that are moving in a straight line. So if an object was moving to the right, we said it had a positive velocity. If the object was speeding up, it had a positive acceleration, because the velocity and acceleration need to be in the same direction in order for an object to speed up. Similarly, if an object was moving to the left, let's try that again, moving to the left. So moving to the left, we said, was a negative velocity. If it was speeding up, it had a negative acceleration, because the velocity and acceleration needed to be in the same direction to speed up. Dealing with linear motion, the positive and negative signs were completely sufficient to describe the direction. Because as an object moved right or left, right meant positive in our typical Cartesian coordinate system, left meant negative. There was no motion up and down if the object was moving right and left. So linear motion, it is as simple as using plus and minus to fully describe the direction of a vector. But we're getting into looking at motion that's not linear. So for example, if we hit a baseball, we know the baseball will fly through the field and either be caught or it will land on the ground somewhere. But overall, the motion of the ball is not a straight line. This is not linear motion. So a plus and minus sign for right or left and up and down is not quite sufficient. And so what we're going to talk about just is introducing vectors in general at the moment. In terms of what we've talked about so far, our vectors are position, displacement, velocity, and acceleration. So we've been using S to represent position. Displacement is our delta S, so the final position minus the initial position. Velocity is V, acceleration is A. For our vectors, any one given vector, for example, in this picture up here where I was saying we were going to hit the baseball, we draw a line with the arrow to represent the vector, which is what we did before. We drew an arrow pointing to the right if the object was moving to the right, an arrow pointing to the left if the object was moving to the left. So we're still going to draw an arrow to represent whichever vector we're talking about at a given moment in time. So if this is velocity, the vector itself, the length of the vector represents the magnitude of the vector. In this case, if this is our velocity vector, the length of the vector represents the speed at that moment in time. And then the arrow points in the direction it's headed at that moment. To fully describe this vector, when we talk about a vector having magnitude and direction, this goes back to polar coordinates. I don't know if you happen to remember. When talking about polar coordinates, we have a point, essentially, in a coordinate system. So x-axis, y-axis. The distance from the origin to that point was labeled r. It could be a distance, it just represented how far from the origin to that point. In this case of the velocity up here, r means the magnitude of the vector. So for velocity, that means just the speed, how fast. And then in polar coordinates, we also label our coordinate in terms of the angle from the positive x-axis, traveling counterclockwise. So when we talk about magnitude and direction, if we think of polar coordinates, we listed a polar coordinate based off of its r and its theta. That is totally valid, and that's what we use if we are describing a vector in terms of its magnitude and direction. That's not the only way to represent a vector, though. If we think about this same coordinate system, x and y, we know this point right here, the dot that my arrow is pointing towards, we know that is a specific x value on the coordinate system and a specific y value on the coordinate system. We can talk about vectors in terms of how far just in the x direction they point and how far in the y direction they point. We call these components. So this would be called the x component, the horizontal piece. The vertical piece would be called the y component. When we write a vector in terms of components, we're calling these specifically rectangular components. Rectangular, which actually, if you look at my little picture here, this dotted line I drew and this one, we actually have a rectangle right here, where the original r vector is the hypotenuse of that rectangle. So these rectangular components, we're saying the horizontal side of that rectangle is the x component. The vertical side of that rectangle is the y component. We can call this top horizontal piece the x component and the vertical piece the y component. It doesn't really matter which side we're drawing these rectangles on. And, well, I guess we have the rectangle. The vector itself has to be the hypotenuse of that rectangle. It doesn't matter whether we call the left side or right side the y component, or the bottom side or top side the x component. When we write our vectors in terms of these components, we represent them and call this version vector notation. For any given vector, we represent how far in the x direction is the length of that x component, and then we put an I hat behind it. I hat specifically means the x direction. The I hat is called a unit vector. It has a length of 1, just the number 1. It has no units as in meters or meters per second. It's just the number 1, and it points specifically in the x direction. When we account for the y direction, we write down how big the y component is, and then j hat. J hat represents the y direction. This is a unit vector as well. It has a length of 1. Now, we're not getting in 3 dimensions, but I know some students take statics either at the same time or shortly after. If we had a 3-dimensional vector, we would throw in what we call the z component. And I put a line through my z's because my z's and my 2's look very similar. So it's my way of distinguish between them. K hat means the z direction. So we use these unit vectors to represent how far in the x direction, how far in the y direction, how far in the z direction. So let's do an example. For example, let's go back and say we have a velocity of, 22 meters per second at an angle of 40 degrees from the horizontal. This right here would be the magnitude and direction. So you want to be familiar with these terms. Magnitude is the 22 meters per second. Direction is the 40 degrees. So direction means an angle. Magnitude means how long is this vector. I want to talk also about writing this in terms of components. So those rectangular components, which we also call that vector notation. When we do that, we need to again remember that we can think of this vector, this arrow we've drawn as the sides of a rectangle. Meaning this vector points x, I'm just going to label it as x right now, some sort of x distance to the right, some sort of y distance up. Typically, I would draw my x, and then where I ended my x, I would draw my y upwards to make a triangle. Those x and y components, those sides meet at a 90 degree angle, which means my trig, my sine of theta, would be my opposite side over the hypotenuse. Cosine of theta would be the adjacent side over the hypotenuse. The tangent of theta would be the opposite over adjacent. It is totally valid if I wanted to go up first for y and then go to the right for x. My right angle would then be up in that top left corner. The important piece is that we're getting a right triangle. Those right triangles are what determines the components, meaning the side that is perfectly in the x direction and the side that is perfectly in the y direction. And again, that can be the x on top and the y to the left. So it doesn't ultimately matter which triangle we draw. I typically draw the triangle that has the angle in there for me. So this x on the bottom, the y going up, I have that 40 degrees in there. I know the hypotenuse, the length of that hypotenuse represents 22 meters per second. So the speed, the how fast at that moment. So knowing the hypotenuse and the angle, we can easily find the sides. For example, we can say that the sine of this 40 degree angle will equal the opposite side, which is the y component side, divided by the hypotenuse of 22 meters per second. Therefore, we can say y is 22 meters per second times the sine of 40 degrees. So let's see, sine, oops. So since I'm only essentially writing down 2 sig figs, I'm going to just write the 2 sig figs here. So we can say the y component. We would call this the y component of the velocity. So we can say at this exact moment in time, whatever object is happening to move at 22 meters per second at this 40 degree angle, we can say that this object has an upward velocity of 14 meters per second. But that doesn't fully describe the total velocity. That's only the y component, meaning the upward component. So we still need to find the x component as well. Looking at the same triangle, the x side is adjacent to the 40 degrees. We have the 22 meters per second still. So I can say that the cosine of 40 degrees would be the x side over the 22 meters per second. So the x component would be 22 meters per second times the cosine of 40. So to round to 2 sig figs, I'm going to have 17 meters per second. We would call this the x component of velocity. To represent that in terms of this vector notation, or in terms of these I hat, j hats, we would say that the velocity vector, this specific 22 meters per second at 40 degrees, this magnitude and direction is a perfectly valid way of describing it, but we might be asked for vector notation. We would say that this velocity vector can be written as 17 meters per second pointing in the positive x direction plus the 14 meters per second pointing in the positive y direction. Oftentimes we will leave the units outside and just write the vector itself in parentheses. So what this vector notation represents is that the object's velocity at this moment in time is 17 meters per second in the x direction and 14 meters per second in the y direction. So two ways of describing our vectors: magnitude and direction, think polar coordinates, the magnitude, the r, angle, theta. In terms of components, which we also call vector notation, is specifically in terms of x and y. And these x's and y's we do need to represent up and down with plus versus minus, left and right for minus versus plus, so we'll go through an example with that as well. You do want to become very familiar with going back and forth between these two forms. Oftentimes we will be given information in terms of magnitude and direction, but when we start working with multiple vectors and wanting to add them together, we will want them in terms of their components, which I'll show why as we continue on. So let's look at another example. Let's say we had a vector that was a distance. Let's say the distance was 40 meters, and they gave us an angle of 35 degrees from that downward direction. So we have a magnitude and direction. Magnitude is just how far, 40 meters. Now direction, typically we write our angles relative to the x-axis, though that may not be how it is given, as we see here. If we want to, we can superimpose a north, south, east, west on here. Or we can just say from a regular Cartesian coordinate system, we can also find the angle. So the angle from the x-axis, 90 minus the 35, would be 55 degrees. And it would be negative 55 degrees because that's below the x-axis. Polar coordinates, remember, always measured from the positive x-axis going counterclockwise. So technically we could say, 270 plus 35, we could say this was at 305 degrees. These two mean the same thing as far as the angles are concerned. Now again, we want to be able to get to components, x and y components. We always start drawing either x or y from the base of the arrow. For example, if I go down, that's going to be my y component. It is pointing downwards, so it will end up being a negative y component. And then I can go to the right. Sorry, I didn't meet up perfectly there. But to the right would be considered the x component. One key thing to keep in mind is the vector itself, this 40 meters, is always the hypotenuse of the triangle. the components, the x and y components, are always meeting at a right angle. So the magnitude of the vector is always bigger than either side. I suppose it could be equal if the vector points exactly in the x or y direction. So the other component would be 0. So again, let's write this vector in vector notation, meaning component form in terms of the components. Again, sine, cosine, tangent are going to come in handy. We now have a triangle. This side's 40. We're trying to find this side and this side. I know this angle. This time we're not going to have cosine being the x component like we did before. Cosine, remember, is always the adjacent side. So in the case of this angle we've been given, the adjacent side is y. The hypotenuse is 40. Now I'm not labeling it negative yet. I'm just going to do the basic trig with my triangle and say that y is 40 meters. I'm not going to write the units right now, but I do need to write it when I'm fully writing out my vector. So we can say that this 40 meters at exactly this 35 degree angle, rounding to 2 sig figs would be 33 meters. So ultimately what that says is if I start at the same point and head down by 33 meters, I'm going to end up lined up with the vector, the tip of this other vector. To fully describe the vector, though, we need to also describe how far to the right. So how far to the right, this x component. In our triangle that I drew just below, just to see it more clearly, this x side is opposite the 35 degrees. So opposite over hypotenuse would be sine. So opposite side is x, hypotenuse is 40. We would say that x is equal to 40 sine 35 degrees. So 23 meters. To represent this in vector notation, from the picture, I can see that I need to go in the negative y direction and then the positive x direction. So I would say that this displacement vector was 23 meters in the positive x direction. I'm going to put my units at the end. To represent the negative y direction, I would say negative minus 33 j hat. Minus j hat means move in the negative y direction. Ultimately, what we're saying to someone, if we start at this specific origin, which represented the original origin, if we head exactly in the positive x direction by 23 meters, and then where we ended, go down in the negative y direction by 33 meters, we will end up where we would end up if we had traveled at 40 meters in the first place at this angle of 35 degrees. Now, by the way, we can totally use this triangle I've just drawn. We could have used that in the first place. Our original picture to the right is our x component, down is our y component. We could totally say from this top triangle that the cosine of 55 is equal to the x component over the 40 meters. This would give us x of 23 meters. It doesn't matter which triangle we use. What matters is that we're being careful in terms of what we mean by sine and cosine. If we took the sine of 55, being the y side, the opposite side over the 40 meters, we would have found that y was 33. The negative sign we have to see from our picture. So we always want to draw a picture. Are we headed right or left, up and down? That's how we decide. Since we had to go downwards, that's why we decided y had to be negative. Because we traveled to the right, x has to be positive. I'm going to end our intro video here, but I will do some more examples for those that want more practice setting up the individual vectors. If you feel comfortable with this already, go ahead and move ahead to adding and subtracting vectors, which is what we're going to be doing a lot of this semester.